per centimeter cubed.
And the accepted value is 7.874. So pretty darn close on that one too. Now the reason why the density of steel is about the same thing. A difference between steel and iron is steel has iron and carbon mixed, whereas steel is iron with carbon mixed in. The density is roughly the same thing, but the reason why I feel more that this is iron instead of steel is the fact that there's just a thin layer of rust around the outside. Steel much less likely to rust. All right, so feeling pretty good. We got iron and we have aluminum. I looked up the specific heats of those and I have it in joules per gram degree Celsius. Water in joules per gram degree Celsius here. So we'll be using that just because that's what I have here. Questions on this before I erase it? We're going to go through a very similar process to what we just did. So if I take this iron block, or one of the blocks, and put it into this water, what do I expect the final temperature to be? Well, let's make our prediction first. First we'll do it with the aluminum. So again, it's MC delta T for the water is equal to the negative of MC delta T for the aluminum. The mass of my water is, let's talk about the mass of the water. I first put in 68.8 milliliters, and that was measured from this. And I poured it in, and then I thought, I'm not sure that's enough, so let's go ahead and add some more. So I added another 34 milliliters. So I had 102.8 milliliters of water. I measured the mass of the empty cup, 3.82 grams. After I pour the water in there, I have 104.48 grams. So therefore, what's the mass of my water? Oh wait, sorry, try that one again. Yeah, okay, mass of cup and water is this. So what is the mass of my water?
That mass minus the mass of the empty cup.
Yep, that minus that.
$100.66
Units.
grams.
Let's see if that matches what we were saying earlier. The density of water would be the mass of the water, 100.66 grams, divided by the volume, which is 102.8 milliliters, which is the same as a cubic centimeter.
0.979128794 grams per milliliter.
And we were using the value of 1, so we're pretty darn close on that one also. All right, so mass of the water, we had, so this is 100.66 grams, times the specific heat of water in joules, since that's what I have over there, that's 4.186 joules per gram degree Celsius, times the change in temperature, which is whatever our final temperature is, minus basically the room temperature. It's been sitting out for a bit, but that's right. We were going to retest that, so let's try to do two things at once here. Actually, what makes more sense, if I pull that out, it's gonna be hot and it's gonna start to cool off. I put it in the water, it's gonna heat the water up some. I'm gonna grab another thermal probe and do the water separately. I will be right back. I'm just gonna let it roll. At least this time I knew where they were. Now, the reason why the water would not be room temperature necessarily is because it was cold to come out to start with. So it's warming up as we go. But the initial temperature of the water, for a level of precision here, I'm gonna go at 20.6. Is equal to negative mass of my aluminum, which we have is 89.67 grams, times the specific heat of aluminum, which is 0.89 joules per gram degree Celsius. T minus the initial temperature of the aluminum. The aluminum has been in that water for quite a while. It is at, it's hovering around 97 degrees, so 97.0 degrees Celsius. Right. So the math problem, so let's drop the units there. So I got 100.66 times 4.186 times T minus 20.6 equals negative 89.67 times 0.89 times T minus 97. That's the math problem. So what first?
Distribute our constants.
What did you say about the constants?
Distribute them into the parentheses.
Let's combine them first
Yeah,
before we
well, yeah.
distribute. All right, so that, what is that right there?
421.36276.
Like 421
.36276
times T minus 20.6 equals, and then this,
negative 0.8063
times T minus 97. Now distribute. So 421.36276 T minus whatever that times that is.
$8,680.0728.6.
Equals, now I got this and that. I got the first one, negative 79.8063 T plus, because I got negative times a negative,
7,741.2
7,741.
and 3 ones. 1.
So now I've got an algebra problem, so let's get all the t's on one side and the constants on another. So I'll add this to both sides and then I'll add that to both sides. So 421.36276 plus 79.8063.
$501.1690 and then a 6.
Times t equals, and then 7,741.2111 plus 8,680.07286. $16,421.
284.
All right. Now we solve for t by dividing both sides by this coefficient here, by the 501.16906. 501.166. And we get a prediction of the final temperature.
32.7659572.
In units?
Celsius. Celsius? Degrees Celsius?
Yeah. All right. Now, this thing is not going to measure that level of precision, so, oops, wow, glad that didn't fall over. So I'm going to take first I'll take the thermometer out just so that you can see Newton's law of cooling. We talked about that the other day. All right, so, that's not what I want. Graph. Show graph 1, okay, good. All right, so, okay, it's gonna go for 3 minutes. All right, so I'm gonna go ahead and start this, and it's giving me a temperature up here. Now I take it out and let it hang out in the air, and you can see that the red line, I'm hoping that you can see the red line, how it starts out with a steep decline, and then it starts to curve as it's approaching basically room temperature, which is the blue line. Yep, there we go. Just make sure it's doing what I expect it to. Okay, it's still moving. For a second I thought it wasn't moving anymore. And that's probably sufficient right there, so if I hit stop, you see a much more distinct curve. I'm hoping that's the, Jennifer, you're the farthest away. Can you see that? Okay. And Dulce, you're next? Okay. So anyway, Newton's law of cooling. So we're going to take the aluminum block, put it into the water, cap it, and oops, I need a temperature probe here. So I want this one. Now, one of the deals with this is we are assuming there's no energy lost into the environment. So we need to make the transfer as quick as possible. So let's get this prep part done. So I need a place to put the probe in. And now the temperature of the water should be increasing as the other one is decreasing. This should be, oh, I'm hearing that, okay. Actually, light. Yeah, trouble is I wasn't in the water before. And by the way, the big cup right there, courtesy of your federal tax dollars. This one. Now, over enough time, it's going to start to cool off. So let's do a little sloshing around here. To mix the water up, so I'm not just getting the temperature in one spot. And I'm using the graph here so that we can figure out what the maximum temperature is. And that looks like that's pretty much steady right there. So I'm going to go ahead and stop. Highlight that. Analyze statistics with the blue temperature. And the maximum, 34.2 degrees Celsius. We're predicting 32.76. Although it did end. Actually, that first value, it must have been touching the block, and that's why it went above our prediction, because if anything, I would expect it a little bit below. However, it did, after I started sort of mixing it around, it did settle in at 33 degrees Celsius, which is pretty darn close to our prediction.
Ooh, close enough for government work for sure.
Darn straight. All right. Let's do this again. I'm going to assume that there's not a whole lot of loss of water here. And why don't I make this hole before we begin? All right, that'll now go through. All right, so let's get this temperature on here. All right, this time, we'll figure out what the temperature is, we'll figure out the final temperature, and we'll predict what the specific heat is. Now, I am expecting the specific heat somewhere around 0.45 joules per gram degree Celsius. So let's get the equation set up. Actually, I only wanted to erase part of that, but well. So I know that the energy lost by the water, or gained by the water, plus the energy gained or lost by the iron should equal 0. The formula, NC change in T, NC delta T of the water is equal to the negative MC delta T for the iron. Just shorten it to F. The mass of the water, still gonna assume roughly the same thing, so we had mass of the water to be 100.66. Specific heat of water, 4.186. Change temperature of the water, we'll get to, so minus, oh, actually, we do need to do this differently. This water's been heated up. That's why I brought along this. All right, so the amount of water that we have in here. Is 94.2. So 94.2 milliliters. And based upon what we had done just a little while ago, that should be about 94.2 grams. So let's go with that. So that 100.66 is not right anymore. It's 94.2 grams. Temperature of the water, 21 degrees Celsius. So minus 21. It's going to be equal to the negative mass of the iron block, which was 248.78, 248.78, times the specific heat, which is what we're going to find this time,